Alright, welcome to way more than you ever wanted to know about carrier landing geometry. So in a previous quest, I dissected the model, the carrier model from DCS, and I had a model from FSX of the F-18. Well, in doing the exercise with those models, I determined that the model of the Stennis in DCS is wrong. It is not only too small, the proportions are all incorrect as well. So I couldn't use that. It'd be really cool to visualize with a 3D model, of an airplane and a deck and seeing what that landing envelope is, but just can't do that. At least not if we want to stay true to real world. So what we're going to do here is build this geometry with all the wires, the distance from the ramp to each wire, distance from ramp to the lens unit here, and we're also going to use the NATOPs. The LSO NATOPs, I've got one from May 2009, and we're going to use some other known pieces of information here, namely hook to ramp distance, hook to touchdown point for CVN 74, so 230 feet from the ramp, results in a hook clearance of 14.1 feet. So in other words, as it flies over the ramp, hook is 14.1 feet over the ramp at a perfect 3.5 degree glide slope, and it'll strike 230 feet, which I just happen to know is between the 2 and 3 wire. But we're going to model this all up in a very detailed way and extrapolate some information from this. So first, we're going to use two pieces of information as the base. That 230 feet is not quite perfectly centered between wire 2 and 3. Perfectly centered is 230.15 feet. Ooh, 0.15 feet, who cares, right? So we're just going to use 230 and 3.5. So come over here to CATIA. So I work in aerospace, so I get to use CATIA every day. Pretty awesome tool. Most planes are designed in CATIA. I'm not sure if the F-18 was or if that was done in NX, but in either case, we're going to have a length of 230 feet here along that horizon. So, all right, that gives us an idea of the scale we're dealing with. And then we're going to put, I want to put a line here and just call this ramp, right? Just a line that I can sketch to. I might as well just go ahead and start labeling these things. So we'll call this one ramp plane, right? Or maybe gate. Oh, you like the word gate? Okay. And then we know this is 230 feet from that to the touchdown point. And then from touchdown point of the hook, we care about it at the gate. We want to check that 14.1. So right now, if you're not familiar with CATIA, when it's greened, it means it's constrained, so it's well positioned. When it's white, it means I can still move it. It's not constrained. So I want to lock that down a little bit more. I can do that by assigning a dimension to it. So I want to use 3.5, angle of 3.5 degrees. So let's double check some tables that we've seen. We want to measure between these 2 points, 14.067. Okay, I'd round that to 14.1, especially considering that's a safety thing. So that's the hook path as it travels down over the deck on a perfect 3.5 degree glide slope, and it lands where it lands right there. Okay, let's build in another thing though. We want to know what the eyeball is doing, because the pilot is ultimately flying his eyeball down a beam of light, right? Woo. So I want those parallel. It's doing an automatic constraint there. That's pretty cool. And there's the other constraint. So I want both of those to hit. I want it to be parallel or actually intersecting that horizontal line, which is representing our, what is that representing? Deck line. There we go. That's the word I'm looking for. And I want to apply a constraint to this and call that parallel. Cool. So now that's parallel. And what else do we know from some information that's published out there? Well, we know that the hook to eye value for an F-18 is 16.7 feet. So I need to constrain that point to that point by 16.7 feet. I want this guy, that guy, be 16.7. There we go. Now it's fully constrained, so it can't move. We know that's along the deck. Interestingly enough, if you're not real comfortable with trig, this triangle here, that length right there, along that horizon as it intersects, there we go, that guy right there is actually the same as the length from there to the optical touchdown point. In fact, let's label those. Let's go ahead and label those. So let's find our first point here. Let's just call the origin up here. We'll call that the hook strike point. And I'll just put in a reminder there. That's at 3.5 degrees on everything being perfect, right? Let's hide those. And while we're at it, we'll hide these other planes. This is meant for 3D modeling, but let's use it for 2D today, especially because it does some pretty quick constraints for us. As I was saying, though, the 16.7 exists here, and if we slide that down, it also exists right directly above the hook as well. So given that proportionality, because I know that distance, I can actually calculate that distance. It just so happens that kind of the computer does it for us. So what is that distance? Let's measure. 273.0425 feet. So this was 230. That's 270. Well, that's kind of cool because that's going to give us our optical touchdown point. So now we've got a pretty good basis of the landing configuration for a perfect glide slope. But let's start putting in some information relative to the deck. So we know lots of things here. We know where every one of these wires are. So let's start building that in. I'm going to put a point here, somewhere, I don't know, there. And we're going to measure from that point to our ramp point, right? We know that's 169.9. Cool. Okay. Did I call that ramp point? Let's call that ramp. Ramp. Okay. And then that point we just made, let's call that wire 1. All right, what's the next one we're going to grab? Well, wire 2, 209.9. That makes sense. I don't know, somewhere there. And we'll constrain from that to there. 209. Whoops. Double clicky. 209.9. Yay, hey, making sense, right? Let's do the third point. Kind of know it's going to be on that side of it, but let's apply that constraint. Sure it's well dimensioned. Whoop. And what does that say? 250.4. 250.4. Whoop. Put in wire 4. Oh, I should label these. Label. I'll label wire 2. Wire 1. Oh, no, I didn't. 1, 2. Wire, I can spell. Wire 2. Wire 3. The labels will be handy later because this is going to get messy. And wire 4. And what is that? 291.2. Don't use the 273.2. That's the barricade, the big volleyball net, right? So we're going to use 291.2 feet. I assume there's some rounding here, but okay, I've got some more information. Well, what else do we know from this deck? We're already here. We know that the ramp to lens unit distance is 486. Go ahead and put that in there. I don't know, somewhere down here, right? And from there to there is 486 on the nose. All right, now we're building a good case here. We've got, there's the hook travel path. There's the eyeball travel path. There's the optical touchdown point. We've got our good 16.7 hook to eye distance. If the graphic helps you, this confused me for a while because, like in aerospace, hook to eye distance, you would think it'd be from like that point, straight line to that point. Not what they mean. they mean something else when they talk about hook to eye distance. Find the good graphic. Is that? Yeah, there we go. Hook to eye distance. So it's the line that's scribed between the two. So this hook to eye distance, as given in the other table that I showed you, the 16.7, assumes a properly configured airplane. So on-speed AOA 8.1, right? Now, the thing with that is that technically, if you change your AOA, that hook to eye distance is going to change a little bit, but for all intents and purposes, I've done some quick math off to the side. Doesn't really change it too much, doesn't really expand the hook strike relative to the eyeball, at least not significantly, I think like 1.5 feet. But anyway, yeah, that's hook to eye distance there. Maybe this graphic helps too, this portion down here. Right, hook to eye distance. So you can have different planes, right, different sizes, but they're going to ride that meatball, that ball of light down such that they get a hook strike configured right between the 2 and 3 wire. But it's that vertical component, that hook to eye distance. And that's only true for a good 3.5 degree on-speed AOA approach. Anything other than that, it starts to vary a little bit. But we're going to assume that the plane's geometry relative to the deck for everything that we're going to explore here, a high meatball, a low meatball, what's the deepest you could go and still catch a 4-wire, what's the distance, in other words, from there, where your hook hits there, and what would be the optical glide slope that you'd fall down to hit that. Same thing for number 1. If the hook just happens to catch number 1 late, where does the optical glide slope come down from there? We're going to drive all that stuff and figure out we can make any more sense of this. Get a good understanding of what we have to do when we fly down that window. So, well, from here, I can already see something kind of interesting here. That's the IFLOLS. I don't know if that's the correct pronunciation of that. But LOLS is LOLS, so IFLOLS, why not? All right, so the optical touchdown point, which is here, sits further aft than the IFLOLS. Nope, I already labeled it that. Let's relabel that, get our labels correctly. Optical touchdown point. Okay, cool. Well, let's see if that makes sense. There happens to be this LSO NATOPS. It might give us a clue as to whether or not that even passes a sniff test. So we've got shore-based workstation. We've got the IFLOLS unit. We've got 6 cells. Each cell contains 2, not cells, that's probably the wrong word. Cell is probably the light bulb. Let's call these boxes. We got 6 boxes. Each box contains 2 lights. And look, hey, flight deck is below the middle of that box, because the middle of that box is going to shoot a 3.5 degree glide slope, and we've got a total swing of 1.7. So half of that is 0.85 degrees up, 0.85 down. We can actually confirm that with, look at this, shipboard workstation, and they give you this. So check that out. There's that optimal 3.5 degree glide slope, split down the middle. Top of amber goes, half of that 1.7 degree swing, 0.85 up. And the bottom of that goes 0.85 down. But we know that the bottom 2 light bulbs there are red. So we only want to be playing in the amber. So, okay, so that makes sense. So I might want to know where that intersects what would we call that? The optical touchdown point. So we really know that the origin of that light as we physically see it is from there. So the IFLOLS unit sits at some angle up here. I'm going to assume that the face of the IFLOLS sits, that it's perpendicular, because that would mean that the face of it is sitting at 3.5 degrees. So let's do that. I've find a perpendicularity there, picked up on it. There's the midpoint. I'm going to constrain that midpoint to the line. Whoops. No. Misclick. All right, let's do that again. Bring that point to the line, make them coincident. Well, now we've got a problem. I don't know the length of this. I really don't know in real life what that should be. But I've got a clue. So since I ripped apart the DCS model, I was able to measure that. I'm going to pull the measurement up here on another piece of paper that I got. So basically, I know the distance from the top of those cells. Go back up to, there we go. I know the distance from the top of that to the bottom of that. Now, when I say I know the distance, what I mean by that is I measured it using the same CATIA software after I ripped the model apart, and I've got a pretty good understanding of what the dimension would be. In game, if you rip apart the model like I did, you'll notice there's no textures for the light bulbs themselves. The face of these units here, let me zoom in on that. The face of these units here are just flat. So they're using a texture and some in-game lighting to make it appear that those as though they are bulbs there, but there's really not. So the overall distance from here to here, I know, but more importantly, I kind of want to know, or actually all I can know, based on some logic and some spacing, knowing that each one of these is equally spaced, and knowing the overall distance, knowing the height of one of these boxes, because I was able to measure that, and the gap between, I know that the center of the top bulb and the center of the bottom bulb are 70.328 inches away. So let's do a little conversion here. So 70.32, look, I've already done it because it knows me. 328 inches to feet. All right, so it's 5.861. All right, so let's apply that to our model. 5.861. Constrain that length. We already know it's centered on there. 5.861 feet. Cool. Well, now it's still not constrained. I need to lock that point in. Whoopsie. Don't think I clicked the right point there, did I? I'm going to lock that point in to the optical intersection there that we calculated from the 486. So make those coincident. Boom. Okay, that makes sense. So the IFLOLS unit sits 46 feet back. I'm assuming that's a rounded number, but hey, that's all I have to do to work with. 486 feet back. I've made a pretty good guess at the height here. I know the optical touchdown point relative to the deck is right there. What was that? 273 feet back from the hook touchdown point. Cool. And all of this is placed correctly. You know what? Let's All right. Well, now what do we need to know? Well, I kind of want to confirm some things, confirm some understanding of the LSO NATOPS here. So I don't have direct data for the IFLOLS, but what I do have is this right here. This table is pretty handy. This table is even more handy though. And here's why I think why. The distance from the touchdown, the vertical beam height of all 12 cells is a certain height. At the ramp, we all know what that means, because I'm not quite sure what they mean by touchdown here. Is that touchdown the hook touchdown, or the eye, or the position of the eye is at touchdown? Because this is all relative to the IFLOLS. I don't know, but let's take a good use some good judgment here. Let's see if we can get to this number and derive that number from what we have now, the current geometry. Well, if I said that point represented the top light bulb, and that one represented the bottom light bulb, I think I probably do know that probably shorts me some distance, because the way those light bulbs work is, I'm just going to make a real quick circle here so you can see what I'm talking about. There is some width of line that you can see, some light that's behind it. I don't know, something like that, where it's not like just this whole thing lights up. That's currently what we have in game. But this whole thing, it actually moves down a light bulb such that I guess this width, or this height of this little light plane, can actually span two bulbs. That's how this would work, because looking back at this NATOPS, right? Going back to that image and even ripping apart the geometry in game, there's a space in between. And if a perfect 3.5 degree meatball is right there, that means no light can emit from there, because there's a gap up there about 1/4 inch. So that means the light's got to be shared from these two units. Okay, that's pretty logical. But all that to say is, in my model here, if I'm short, which I probably am biased short, I'm missing a whole half a diameter up here and half a diameter down there, basically such that I get this case where I can barely see the bottom of an amber or barely see the top of an amber, but still, that's all I have to work with. So that means there is a focal point, some position way back here, that this line going down at 0.85 degrees relative to the center line, and this line 0.85 degrees relative to the center line, meets at some focal point. Well, let's figure out what that focal point is. Now you can do the math on it, so certainly because we know these proportions, and I've done this on paper, it's boring to watch on paper. It's much more fun to watch this. I know this height, and I know that. I know this this angle here. I can know this slant distance, and I can back calculate based on the relationship of this height, which is half of that, and the angle that I have, 0.85. I know the focal point is going to be way back here somewhere. Let's see if we can draw it, though. I'm going to put in an arbitrary, there we go, something, I don't know. It's picking up the extension of my center line, so I'm going to click there. And you know what? I'm going to constrain that angle, because that will fully constrain it. So I know that from top of this to bottom of this is 1.7, but half of that is 0.85. Hey, what do you know? That's fully constrained now. And so that, by definition, has to be the focal point. We'll confirm it on the bottom. Check this out. From the bottom of that light bulb, all the way back here, we'll make them match. And what do we see? I bet you if I measure the angle of this relative to the center line, what do you know? 0.85 degrees. So that, by definition, back here, is our focal point. That's pretty cool. Now I'm going to go ahead and add as if I didn't have enough lines, add a deck line. Going all the way out, representing our deck. We'll make it stop in line with our focal point there. We'll come down. Ooh. Okay. Got enough lines here. Let's quickly make sure we're still tracking here. There's the end of the ramp. There's the deck. There's the hook travel path, I travel path for a perfect 3.5 degree glide slope. So that's 3.5 relative to the deck. This is parallel, so that technically means that's 3.5 relative to the deck. Got all my hooks, or all my wires in place here. We know a whole lot of information just from the deck layout. I know where the center of that is. And so really the only thing I've made an assumption on is the height. But we're about to compare whether or not the height that I picked will result in a good window out here. In other words, the window from top of amber to bottom of the red, if that matches what we see in the NATOPS. More specifically, whoops, blew right past it. More specifically, this dimension, 20.4. The vertical beam height of all 12 cells, 20.4. I assume when they mean vertical in the sense relative to the world, not the IFLOLS unit, like vertically along the triangular path. You can do that, visualize that geometry in your head real quick. So I'm going to do a line coming out of that. Make sure it's parallel. Yeah, I can see that other edge turn orange. Boom. Okay. That was a whole lot of zoom in there, but I know it's parallel to that. It turns orange when it gives you a parallel indicator. And I'm going to draw from that guy. And go there. Okay. So we already know that that's 0.85 and 0.85. We know the distance between these two is 1.7. Let's just make sure that that those parallelisms applied. Yeah, 1.7, good. So now I want to check that vertical beam height. So let's do a quick measurement there. 20.346 feet. Okay, I'm a little short. Like I said, I didn't include the half of the diameter of those bulbs. Maybe that's where it's coming from, or maybe I've got a completely wrong understanding of how those light units work. But 20.346 relative to 20.4. So I was off 20.4 minus 20.346. Let's call it 3.7. So I'm 0.053. You know, I think this has a converter in here. I've never really done it before. So we've got feet to inches, 0.053. Ooh, 636 thousandths, so about 5/8. 5/8 of an inch, a little over 5/8 of an inch off. Oh darn, and oh, by the way, that tolerance is split between the top and bottom, so I think that's close enough, all right? All right, so we've got a valid model here now, right? A lot of lines here, I do realize that, but so you can't just necessarily jump in the middle of this video and pick up how we've come to this so far, but still, now we've got a good model here. I'm curious to know just how far below the deck the optical focal point for that is. Let's do that. 11.016 feet, so 11 feet. And we know it sits, let's see, we know where that unit is in game because we can see that. Well, how far back is the optical touchdown point? Not that you should ever spot the deck. Don't ever spot the deck. Ride the meatball, right? Listen to the meatball. Is 17.0425. If the deck pitches, all this changes, by the way, guys. So 17 feet back. So I wonder how far back, that would be interesting to know how far back that focal point is. So from that point back to along the deck, 197 feet. Interesting. 197. What was that? 273, and then 230. Hey, I know the overall length from there to all these points. That's cool. Okay. Well, as if that weren't exciting enough, let's start looking at what would happen if we started flying our eye path down these upper and lower limits here. Actually, there's one that we need to add in here. This is bottom of amber, and we know we should never ever fly down that, but it's implied that we can certainly fly down a bottom of amber. So we'll start at our focal point, and we know that bottom of amber is between the 3.5 degree glide slope and the bottom of red. So we'll put that somewhere in there, and now we'll constrain it. But let me remind myself of the LSO NATOPS here. There we go. So I can either constrain it 0.4 degrees up from the top or 1.3 from the top of amber. Let's do 1.3 from the top of amber. I just like the way that constraint sounds. Don't like the red. The red's no good. I'll avoid that. So, oops, didn't want to actually measure it. I want to actually apply a constraint that would lock that dimension in. Hey, that was pretty close. 1.3. All right, so that would be, this is all eye point now. The only one here that I've shown so far ascribed as a hook point is this guy. That's the hook point for a 3.5 degree glide slope. And that, by the way, this parallelism will exist for all conditions, but this will not. The 16.7 technically would change. Now, here's where I'm about to make another assumption, because I don't have the dimensions. I can't pull apart the DCS model of the F-18, and I don't have access to drawings for the station line and water line of the eye and the station line and the water line of the hook. That's aircraft speak for the coordinates of those 2 points. If I knew those 2 points, I could just draw a straight line distance. So here's what I mean by that. There's the eyeball, and there's the hook. But we know that the plane sits at some angle such that the pilot's eyes are here when the hook is there. So pilot's eyes are up here. The pilot's eyes are not up there at that point when it crosses this ramp plane. They're somewhere in between. Well, I've done some analysis using side views of F-18, so basically like poor man's photogrammetry. And I've looked at the model that FSX had, and with the hook deployed, which I did have to model that in, but I took a pretty good guess at the angle of that hook deployment. So I know eye point, and I know hook point in the FSX model, and I determined that distance, true distance between eye and hook, is 36.5 feet. Hey, if I'm wrong and you know that, hey, let me know. Then we could correct the model, but I feel pretty good about that. So the eyeball's here, the hook's there, you know, nozzles are there and the nose is, I don't know, somewhere there. But hey, we know that distance. Well, what I also might want to know for later reference, and I'll even do this as a reference line so we barely see it, because I only need it parallel to the deck here. I want to know what the angle between the hook and eye angle, hook and eye point, and the, oops, not that one. Do it from here to here, because it's already well constrained. All right, why is it giving me that 0 feet? Don't care. Okay. Yay. Okay, that is not the angle of attack of the airplane at all, because angle of attack has to do with chord lines. So this already has, if the jet was sitting flat, let's see if we can look to that, look at that geometry. If, when the jet's sitting flat, center line is here, or horizontal line is here, there's some angle, some height difference over some length between these two. What I've done is basically drawn the hypotenuse, if you follow me there. So that's at 0 angle of attack. Let's assume that this sketch here is drawn at angle of attack 0. So we know that there's going to be, this whole thing gets rotated up 8.1 degrees, and that's if you're flying level, but we're flying down a 3.5 degree glide slope, so 8.1 minus 3.5 is 4.6, roughly. Don't know if that lines up with this, but really doesn't matter, because what I do know, geometrically speaking, is that that's the angle, and that's what the plane looks like relative to the deck. That length is never going to change, but that angle is always going to be there if you're flying down if you're perfectly configured, you're on speed AOA. What can vary is which meatball light you run down, right? So let's look at what would happen if we take the same 36.5 degree, let's just simplify this and call this the plane, at an on-speed AOA, which results in that. I realize that doesn't make much sense for the terms we're used to speaking in, but bear with me here. And let's figure out things like, I don't know, hook clearance and things of that sort. So if this is the bottom of the amber. If we ride the bottom of the amber all the way down, ride the eye point, because remember, we can't really, we only control the hook via our eyes riding down that meatball. We're not, so therefore we aim the hook, but we're still riding down that beam of light with our eyes. So I have no clue where this is going to go. The methodology I used earlier was a little different, but I know it's, I don't know, something like that. Let me turn off the reference line so we can actually see that. And I'll give it some length, right? 6.5. Cool. And then now we'll set the angle. What was that? And this is the one I actually have to read. And I'm going to put all the decimal places, because why not? 26.673136. Yeah, I get a lot of these don't really matter. I work in fractions of inches every day, so a thousandths to me matters. I just turn on more decimal places than needed sometimes, so I can know what that last figure is. Sometimes we get into lower points than that. Angle-wise, we usually hold plus or minus ½ degree. Depends on what it is. But anyway, so I've basically duplicated that plane at proper on-speed AOA. Down here, ridden that lower amber meatball all the way down. Hey, and where does that strike? Strikes some distance before the one wire. That's kind of scary. 33 feet before. Well, it just turns out that the distance between these is about 40. So that's almost like, wire, if there were wire 0, it'd be like right there. Let's see if this passes another constraint though. So just because you get an amber meatball, lower amber meatball, I'm concerned about it meeting the 10-foot deck height limitation. So because I know this is the lower amber glide path, I know the hook has to travel along that same path. All right. Let's see if I can pick the correct parallelism here. Not that one. Hey, do you see it snap there? There we go. Whoop. I could apply it manually, but if I get it in the first take, that's good. So I know that's the path the hook has to travel for a lower amber meatball, for an eye riding a perfect lower amber meatball with correct on-speed AOA. Basically, you found that light bulb early in the groove and you rid nothing but that down. Where does that end up? Well, that looks short because we know that distance from there to there is 14.1. That looks like darn near half of it. But we have these cool measuring tools, so 7.26 feet. What do you know? It violates that hook to deck minimum safety clearance of 10 feet. That's not good. So you can ride that 3.05 degree meatball down and still be wrong. So that's why we have LSOs, I assume, right? So they make sure that we don't get in a configuration where we're short at that position over the ramp. Now, I guess it's possible to be correct over the ramp, but then fall into it, right? You've got a descending meatball. That's what the pilot's eyes would see. Okay, so we don't want to do that. That's no bueno. Let's figure out how to get that 10-foot, what a 10-foot safety clearance would yield, what wire that would put you on. Oops, don't want to do that. Hey, let's save. We haven't done that in a while. All right, so let's put a point on here, and let's constrain that point to the deck. And yeah, it was 11 feet. Call that 10, lock that in. And now let's put a... Well, I can't do a hook all the way down because it's still to the pilot's eyes. So what I'm going to need to do is build another little fake airplane here. And it just so happens to be parallel with that. That's true. It's going to be parallel at that point. And this is, again, same distance. Plane didn't shrink. 36.5 feet. Cool. Well, that's my eye point at a minimum hook clearance of 10. Well, that sits just above the amber meatball. Not by much, but hey, let's be really specific unnecessarily. Or depending on if you like just the analysis sake of this. And shoot this all the way down to the focal point. Holy cow. We got lines on top of lines, but you can't jump in the middle of this video. So, again, that's 3.5 degrees. That's bottom of amber at 3.05 degrees. Wonder what that is. Let's measure it. 3.1425 degrees. Cool. All right. So we're narrowing down the acceptable range that if we, I guess, didn't have an LSO to correct us all the way in, to prevent us from doing a low amber safety violation, then we'd need to know it's there. All right. Now, what happens if we ride a... Actually, you know what? Let's see where that hook strike is. That's what we need to do. Grab another line. Oh my gosh, we got so many lines here. I don't know where it goes. I'm going to put it down here because constraints are getting hard to do, and I'm going to put it parallelism with that. Holy cow. Didn't make it long enough. Somewhere in there. Where does that hit? I can break this with that. Can't I? Ooh, now you're going to watch me struggle with CATIA. Oh boy. I'm going to break this. That. Break point. Yay, cool. So now I know that that point is what? Certain distance after wire 1. So, 12 feet. I don't know. About a fourth of the way up. That's hook strike point at minimum 10-foot safety clearance. So, that kind of tells us something, ladies and gentlemen. That you should never, ever, ever hit a 1-wire, right? All things being equal, right? So the only way you hit a 1-wire is you come over the top of that at something higher than minimum, of course, assuming you're not violating that 10-foot distance, and then you basically settle. So you'll never hit a 1-wire. I guess, maybe, I'm just speculating here, that's why some of the new carriers are 3-wire carriers. I don't know. I don't know if that has anything to do with it. Cool thought, though. Okay, so now we know minimum. Hey, if you're meeting the safety clearance of 10 feet over here, your hook strike's there, and it's a 3.125 degree meatball. Okay. I kind of took some tolerance off there. Now what happens if you ride a 4.35 degree angle all the way down? Holy cow. Now, the lines are getting crazy here, aren't they? But I think you can follow along. If your eyes have already glazed over, then you've probably clicked off of this already. But okay. If you're here, you're probably a nerd like me. All right, now we have to constrain that angle down. And like I said, all this is, it could be wrong. The 36.5 foot, that we're off by a couple feet, then some of this is going to be off, certainly. But hey, it's all I got. I've got an Inquisition in, see if I can get station line and water line for hook and eye, so I know that distance. And I want to get angle of attack relative to those station line and water lines. But that's all I got so far. So if I put that jet with the pilot's eyes at the top of the amber, do I miss the 4-wire? I missed the 4-wire. What do you know? How much do I miss it by? 21 feet. So basically half the distance between the wires. Okay, that's kind of unexpected. You would think that riding, as long as you see the meatball, it'd result in a trap, at least on the top end. We've kind of deduced, at least from doing the math here, with some pretty reasonable assumptions, and a valid window, by the way, which means my IFLOLS height is pretty darn valid. We've already kind of figured out what the lower envelope is, that it's not really the bottom of the amber, it's somewhere north of that, right? Another 0.09 degrees, which is almost, I guess that's another light, because each light is 0.13 degrees. And you're like, why are you caring about such small angular difference? Well, it's because each light is a small angular difference. The first 10 cells here are the amber ones, the bottom 2 are the red. So 0.13 times 10 is 1.3, and 0.4 you get 1.7. This is not, the drawing's not meant to be taken literally, because the way they've depicted this would actually intersect the light coming out of here, and that doesn't make sense. So yeah, take that with a grain of salt, because it's not meant to depict that level of accuracy. We kind of had to derive that, right? So, but we know that, hey, that 20.4 value is good. All right, so, well, if riding the top of an amber meatball doesn't land us at the 4-wire, what will? By the way, that is parallel. There's 0.5. Okay, that kind of makes sense. So something less than that, but how much? I don't know. Figure it out. That goes all the way to the focal point again. And let's figure out that angle. That angle relative to the deck. 4.095. How about we just call that 4.1? So that's kind of interesting, because although the meatball, reading this would maybe lead you to believe that as long as you're within amber, you're going to result in a trap. That's apparently not the case. So this is 4.35, and this is 3.05, but we've already established that the real limits for that, with including the safety limits, is not 4.35, it's actually 4.1, so we're losing a whole, let's see, 4.1, 4.35, so that's what, 0.25? So that's almost the first 2 bulbs you don't get. Yeah, you don't get those. So if those first 2 bulbs are on, then you're probably going to miss the 4-wire. So we don't want to be in there. And what about our lower limit? 3.05 to 3.14.9. So we've basically almost all of that lower amber meatball. So we don't want that. So really the only ones that are valid may be the wrong term there. The ones that we need to care about, there we go, that's a good image. Those are the two red ones. We've kind of said that most of the bottom one is no good. These top two are no good. That puts you over the 4-wire. The middle, a perfect middle meatball is going to be some light emitting from, let me zoom in further, some light emitting from there and some light emitting from there. But we know that those two are right out. These three are right out. We've only got 1, 2, 3, 4, 5, 6, 7 meatballs. And the way the game does it, it sequentially just lights these entire things up. It's probably just a technical limitation of the game that they can't do that little, horizontal beam of light emitting through all of these. But certainly there's a bit of optical wizardry going on there because of obviously this thing sits offset to the center line of the angled deck, 86.3 feet. So it's doing corrections to make all of these numbers valid at the center line. At least that's my understanding. So in other words, it doesn't just project out here in an arc fan and then result in, worse numbers the closer you get. It's doing some sort of correction to make sure all these numbers are valid at center line. If we weren't talking about center line here, then the entire book here, with all these numbers of where these points are, would be invalid. That wouldn't make any sense. Nobody would want to do that. So, hope you found that interesting. I know I did, because I just wanted to understand kind of more about the window. Everyone talks about the 2-foot box that the pilot has to put his head through or his eyes through. I get the sentiment with that, but looks like that's not correct. That's not even correct to their own manual, because back there, if that's 20.4, we don't get to 2 feet until like past the IFLOLS, because that was what, 5 feet. So 2 feet's way down here. So you're not quite flying through a 2-foot box. Sorry. It's still pretty friggin' narrow. I mean, who are we kidding? That's really narrow. But still, interesting. Hopefully that helps your understanding. I know it helped mine, because I used to have crazy notions that, the 3.5 degree, or basically the emission point, let's call it the focal point, was at the touchdown point. I don't know why I thought that. But yeah, that led to some really small numbers. I'm like, man, that's really tight. How do you even fly down that? But yeah, hopefully this helps. We'll see what I can do with a revised model when the new carrier comes out. Hopefully that will be dimensionally accurate. But right now, the one frustrating part in doing this and knowing that the carrier model is incorrectly dimensioned, I wonder if I can bring that up. Yeah, knowing that has been kind of frustrating now that I'm doing case 1s. Just because, well, I can probably do a file, new product. Just because I'm not sure what's true. Like, is the meatball giving me good data only for wire 3? What's really going on here? I'm thinking and trying to do something at the same time here. We're going to go insert existing component, put it there, and we're going to pull up. Whoopsie. Oh. Thought I could put that in. I just oh. Anyway, I was going to show you that model, and I still kind of want to. If you're got the information you need, you can bail from this video, but I want to show you the model of the carrier, and kind of talk over the things that I found to be wrong. Which one should I use? Yeah, let's see if this one loads. And so many different attempts at this. So much frustration with ultimately coming to realize that the carrier model was incorrect. It's too short. The distance from ramp to the touchdown as depicted in game is wrong, so your clearances are invalid there. It doesn't really make sense. Um, uh, the space between the wires is wrong. It's not 40 feet. It's like 36 or 37 feet. I'm not even sure where the IFLOLS is relative to the deck center line. That could be off, but I would hope and trust that at least what they did is, well, I do know that they gave proper dimensions for top and bottom of amber or top and bottom of the whole display. Where that emission point is, not sure. Well, actually, we would know that based on the geometry that they depict in game that I used. So let's assume the same IFLOLS height, because let's assume they got that right. But I would assume that it would put you down between the 2 and 3 wire. But all this other business that we've just done doing the, oh, that's 10 minutes. No way I'm going to do that. All this other business that we've done with, calculating min and max conditions here, what the min and max envelope is, considering safety factors, it doesn't, there's no point in doing that because it's not authentic to what's really happening, at least in the model. It's kind of a moot point. Like it's a fake carrier. What does that mean if we're gonna, play the game? Let's call it authentically because it could never be realistic. If we want to play it authentically and try to follow some of these numbers, then what you're experiencing in game is kind of lying to you. Oh, here's some of the deck modeling. So yeah, a whole bunch of tessellations on there. You can imagine when this thing fully loads. But yeah, all wrong. These wire-to-wire distances are wrong. Probably quickly do that. That wire to that wire. 37 feet. Yeah, it's not 40. So this whole thing I found to be generically, the whole thing is undersized. I had to increase it by 5.5%. There's the IFLOLS light planes that they use. Each one of these like turns on as you pass through it. But yeah, kind of sad to realize that because thought I was authentically flying a case 1. Authentically getting good wires per a meatball condition, and that may not be true. If anything, if the new model comes out and it's all correct, dimensionally accurate and everything, and we can really use the NATOPs and all these clearances and everything, then what that means is that we were actually gaining some bonus tolerance there because the wire distances are wider, or wider by like 10 feet. May not matter much, but I don't know, kind of matters to me. I don't know, I think it's kind of cool. But yeah, let me save this one time and we'll call it quits. Thank you.